Differentiable Monte Carlo tracing through edge sampling. This is a work published in 2018 at SIGGRAPH Asia. These days we know pretty well on how to render a photorealistic image from a 3D scene that consists of camera, geometry, material, and light information. However, going back forward is much more difficult. Given one or more images, can we generate a 3D scene such that when we render the scene, we get the images back? Inverse rendering is important since we often want to reconstruct 3D scenes from images and re-render them, say for robotics, virtual reality, or lightning design in movies. Also, both direct and reverse rendering has great potential for deep learning so that the neural network can understand the 3D information of the images. For this, we need to compute the rendering gradient. However, computing the gradient of rendering is challenging. In general, this is because the rendering integral includes the visibility terms that are not differentiable. For example, taking one pixel from a rendered image, we know the color can be calculated from the rendering equation, where K denotes the 2D pixel filter and L denotes the radiance. The integral usually does not have the closed form solution in general. People usually rely on the Monte Carlo estimation to approximate the pixel value I. However, we cannot take the naive approach of applying the same Monte Carlo sampler to estimate the gradient, since the scene function f is not necessarily differentiable with respect to the scene parameters. Here is a more intuitive example. If you move this bunny a little bit, you need to consider the pixel changes of the boundaries, and also you need to consider the shadow, how the shadow will change. Therefore, it's difficult to calculate the gradient with respect to the scene parameters, and the major challenge of the differentiable rendering is the visibility term. Previous works on differentiable rendering focus on specific cases such as the face or hand, which are hard to generalize. Recent people have worked on fast approximate general differentiable renderers. However, these renders are based on simplified material models and do not compute shadow or global illumination. While these works also approximate the visibility gradients, no general physically based differentiable renderer exists. In order to produce photorealistic image, it's important to simulate how light bounces between the surfaces in the scene. This paper develops a general differentiable physically based renderer, which accurately simulates the lighting phenomenon such as glossy or mirror reflection, shadow, and interreflection between surfaces. There are two key insights of this paper. The first one is to compute the integral and rendering gradients correctly using Monte Carlo sampling. It also handles the geometry discontinuities through a novel edge sampling approach. Finally, this paper shows their utilities in synthetic data and several real applications such as inverse rendering and producing 3D adversarial examples. It also produced more accurate gradients than two previous differentiable renderers. The way we do rendering these days is to randomly sample light paths that go from the light sources to your eyes for each pixel on the image. We will collect many samples per pixel and take the average of them. This procedure is in sense the rendering equation. In general, these individual light paths are not differentiable everywhere, because sometimes you hit the bunny and sometimes you hit the walls. However, the average color of these light paths is actually differentiable. To understand it better, let's focus on one pixel, assuming there are only two triangles in the pixel to simplify the problem. Usually, there are much more triangles and much more pixels. However, we don't know which triangles are in which part of pixels. What we have are these pinpoint samples, which correspond to the light paths I showed before. This is basically the Monte Carlo estimation of the rendering integral. So the question is, what's the color will change when the blue triangle moves up? So therefore, the key insight is, in addition to the pink area samples, we also sample the edges of the triangle so that we can capture the changes at the boundary. This is basically called the edge sampling. If we look at the small neighborhood of the edge samples, we will see the edge sample nodes after the triangle moves up, it will fall inside the triangle, so there will be more blue and less white. This approach can also handle the occlusion case correctly. To formulate this idea mathematically, let's first model this triangle edges as step functions. Here, x is the pixel coordinates and y is the pixel color. Assume the same function f is a constant 1, therefore each pixel is actually an integral over the step functions s. So therefore, when we take the gradient of this integral, we obtain the derivative of the step function, which is a delta function. Delta function is a 0 everywhere except is a single point. In the yellow point, it's infinite. It only becomes a real number when you're integrating it. Therefore, when you use these pink points to estimate the integral, the problem is they will always miss the delta signal, which has 0 error. So the age samples are implicitly integrating the delta function, actually. In general, we will have a smooth shading function f multiplies the step function s. The shading function f encodes the lightning information, like the distance fall-off of the lightning and the material response. We also handle the shading derivatives correctly by combining error samples and age samples. You can see this by applying the product rule. The first term, which contains the delta functions, and the second term, which is the smooth functions, a smooth shading derivative, and it can be estimated by the pink error samples. So basically, by combining this two sampling approach, we can get the approximation of the gradient in the integral. To recap, when we want to compute the gradients, traditional error sampling meets the boundary and cannot handle visibility changes. The key idea in the paper is to implicitly sample the delta functions on the edges. So all the discontinuities happens in the same edges. So we need to formulate the edge using the alpha functions, which is a line or a plane. Then we could write the same function as two parts, fu and fl, where fu and fl are two continuous functions. We have these equations I by using the linear properties of the integral. Finally, we can take the derivatives and using the chain rule, and we have the following equations. The first term is include the delta function, which can be approximated using the age sampling. And the second term, you have the gradients of the smooth f functions, which can be calculated using the traditional error sampling and auto differentiation. This idea can be generalized for computing the gradients for shadows and interreflections between surfaces. It's just integrating in a different domain, like the area of a light source instead of the pixel area. This paper also adopts previous work to use important sampling to sample important edges and pick important points, such as is scalable to the real object and complex things. They first verify their approach on several synthetic things, which covers a variety of effects, including occlusion, non-Lambertian materials, and global illumination. Specifically, they try to match the same parameters of a synthetic image by updating the same parameters. In this example, the goal is to update the vertices of two triangles to match the target. From the video, we know this approach can handle this occlusion correctly. The second example is to optimize the triangle vertices of the shadow blocker. Note that the images in the optimization procedures are much more noisy. This is because they use less samples in the optimization, as they need to render the image many times during optimization. So using the less samples will speed up the process. Similarly, they can optimize other parameters such as the camera pose and the material parameters. And they can also optimize the logo translations and other more realistic things. Apart from the synthetic examples, they also evaluate their method on a real photograph. So basically, at the center is a photo of a room. Someone manually modifies the things, and they try to recover the camera pose, the brightness, and the light sources, the reflection, roughness of the objects. They can see that you can see it can reconstruct the things and match reasonably with the target. It's not perfect, but it does a reasonable job. Here is the optimization procedures. Note that they rendered early iterations in lower resolutions to avoid trapping in the local minima. Here are the visualization of the gradients with respect to the different scenes parameters such as camera and light. It shows that the proposed render could produce reasonable gradients that capture the boundaries of the scenes. They also use the gradient renderer to produce 3D adversarial examples. Here, they optimized over 2,000 parameters, including the vertical positions, camera pose, light intensity, and the positions. They rendered the image and threw it into a popular VGG16 neural network. This network set is probably a straight line with a 53 confidence. They try to reduce the probability of the straight line using the gradient, and after 25 iterations, and the network can be fooled fully by this new generated thing. There are some limitations of this work. First, due to the changes of finding all object edges and sampling them, it's usually very expensive to render a complex things. Second, there are several assumptions of this work, such as there are no interpenetrating geometries and parallel edges, and this paper also doesn't deal with the motion blur and the shader discontinuities. Following this work, there are several papers working on the differentiable physically based rendering. They aim to address the discontinuity problem in the rendering equation either by following the similar approach, but extend to handle volumetric light transport or reparameterize the integral to avoid discontinuity. Another recent work proposed to estimate the derivative of the path integral formulation, which provides a new theoretical framework to estimate the gradient with respect to the scene parameters. Finally, let's recap the contribution of this work. This paper proposed a general physically based differentiable renderer, and two main points of this paper is the first one, the paper proposed a general differentiable path tracer that used the Monte Carlo estimation to approximate both the integral and the gradient of the integral. And the second, it proposed a novel edge sampling approach to handle the geometry discontinuities. Finally, this paper demonstrates their utilities in real applications, such as inverse rendering and producing 3D adversarial examples. And it also shows it can produce better, more accurate gradients than previous work. This is all the introduction of this work. Thank you very much.